To finish up our discussion on the atomic nucleus, we will discuss nuclear fission and nuclear fusion. To this day, I still have to think about these terms when I discuss them so that I don't confuse their definitions. I think fusion is easiest to remember because most of us understand that fuse means to combine together. Fusion occurs when two light nuclei fuse together to make a heavier nucleus. Fission occurs when a heavy nucleus splits into two or more smaller nuclei. Before we discuss these nuclear processes and how they are used, I want to bring your attention to something using the isotope carbon-12 as an example. Carbon has 6 protons, hence an atomic number of 6. Since the mass number is 12, we know that this particular isotope of carbon has 6 neutrons. The combined mass of 6 individual protons and 6 individual neutrons is 12.09570 atomic mass units. Okay, well, the mass of a carbon-12 nucleus, composed of 6 protons and 6 neutrons, is 12 atomic mass units. That is odd. I thought mass had to be conserved. Isn't there the law of conservation of mass? And science laws can't be broken. Where did that mass go? Think back to the star life cycle unit. What happens to the mass during a nuclear process like the one that occurs in stars? Let's see if we can remember. The difference between the mass of the individual protons and neutrons and the mass of a carbon-12 nucleus is 0.09570 atomic mass units. This is known as the mass defect. This mass has to be accounted for because the law of conservation of mass is for real. Matter cannot be destroyed, or created for that matter. Well, do you remember this famous equation? Energy equals mass times the speed of light squared. This is Einstein's famous equation relating matter and energy. Matter and energy are two sides of the same coin. This means that when protons and neutrons combine to form a nucleus, some of the mass defect, is converted into energy. A very small amount of mass is converted into a boatload of energy. A mass defect occurs during the processes of nuclear fission and nuclear fusion. That is why these processes release so much energy. So let's talk about fission. Nuclear fission occurs in nuclei containing a lot of protons and neutrons, like the nucleus of a uranium-235 atom shown here. The strong nuclear force dominates if the nucleus maintains a spherical shape. Natural wiggliness of protons and neutrons can sometimes produce an oblong-shaped nucleus. In this case, the repulsive force may become the larger force, causing the nucleus to release a bunch of energy and maybe some neutrons, and then split into two smaller nuclei. This is fission. As we will discuss more in a moment, the fission process can be helped along by bombardment with neutrons, as you can see in the diagram. The collision can cause the deformation of a nucleus that causes fission. The process of fusion requires insanely high temperatures, but the result is nuclei with a handful of protons and neutrons combining together. Ridiculously high temperatures are needed to get the nuclei moving around so fast that the repulsive electric forces between them are easily overcome. For the moment, temperatures of millions of degrees are only obtainable in stars, like our sun. Therefore, the process of nuclear fusion only occurs in those large nuclear furnaces in the sky. Remember, stars like our sun are fusing two isotopes of hydrogen together to form a helium nucleus. During this process, a neutron is also released. And oh yeah, so is a boatload of energy. Our average-sized sun converts 657 million tons of hydrogen into 653 million tons of helium each second. Now hold on a minute. What happened to that 4 million tons of mass? That's right. That mass defect was converted into energy. A lot of it. So that was a brief explanation of the processes of nuclear fission and nuclear fusion. But how do you know if an isotope will undergo fission or fusion? To answer this question, we are going to analyze this graph of binding energy versus mass number. Binding energy is the energy that holds a nucleus together. Nuclei with a larger binding energy are more stable, meaning that the nucleus is less likely to split apart or fuse together. Now I know what you're thinking. Schmeck, this is not making any sense. That is exactly what I thought the first time I saw a graph like this, and my teacher tried to explain it to me. So let's draw upon some prior knowledge. Remember the FE26 game? We used the game to simulate the process of nuclear fusion in stars. The score represented the mass defect being converted to energy as the isotope blocks slammed into each other, fused together, and made new elements. Well, the heaviest element you could produce from the process of fusion was iron 56. Now, if you look at the graph, iron 56 has the highest binding energy per nucleon, which means it has the most stable nucleus of any atom. There's no need for iron nuclei to keep fusing because that would produce nuclei with lower binding energy. There's also no need for iron to fizz or break apart because that would produce nuclei with lower binding energy. When the amount of iron 56 reaches a certain point in a star, the fusion reaction stops. The fusion pressure pushing out on a star decreases as the star cools. Gravity becomes the dominant force and the star collapses. If the star is massive enough, kaboom! Supernova! So the fusion reaction in a star can only produce iron 56, which means all the elements in the universe that are heavier than iron were produced during supernovas, where the forces are large enough to slam large nuclei together to produce even heavier nuclei. I really hope that helps you make sense of this graph. Basically, all isotopes want to achieve a nucleus like iron 56 because iron 56 is stable. Lighter elements like hydrogen, helium, and carbon can achieve a higher binding energy, which means a more stable nucleus, by fusing together. Look at this large increase in binding energy that occurs when hydrogen fuses into helium. Similarly, heavier elements like uranium, bismuth, and tin can achieve a more stable nucleus, higher binding energy, by splitting apart. You can see how the binding energy increases as you move from uranium to iron on the graph. Another thing to notice is that the change in nuclear stability or binding energy is much more drastic for lighter elements that fuse together than for heavier elements that split apart. Well, binding energy can also be defined as the energy that is released when nuclei fuse together or split apart. What that means is that the process of nuclear fusion is capable of releasing much more energy than the process of nuclear fission. All right, let's switch gears and talk about the uses of nuclear fission and fusion. Humans have harnessed the energy released from nuclear fission in nuclear power plants and nuclear weapons. The only difference between these two applications is control. In one type of nuclear power plant, uranium-235 is forced to split apart by bombardment with neutrons. When the uranium nuclei splits, more high-energy neutrons are emitted. These high-energy neutrons collide with more uranium nuclei, causing them to fizz and release even more neutrons. In other words, a chain reaction occurs. In a nuclear power plant, this chain reaction is held in check with control rods, which absorb some of the emitted neutrons and prevent them from triggering the fusion of another uranium nucleus uncontrollably. Well, in an atomic bomb, this same chain reaction occurs unchecked. This explains the tremendous energy release of an atomic bomb. On Earth, we have the ability to indirectly harness the energy from the sun's fusion reaction by the use of solar energy. Nuclear fusion is not yet possible on Earth because the temperatures necessary to sustain the fusion process are only attainable in stars. Well, I take that back. The necessary temperatures can be attained on Earth, but only inside the explosion of an atomic bomb. Unfortunately, scientists recognized this during the Manhattan Project and were able to produce a hydrogen bomb, a nuclear fusion bomb. The U.S. test detonated its first hydrogen bomb in 1952. This type of bomb is 1,000 times more destructive than the atomic bombs used in Japan at the end of the World War II. Thankfully, this type of weapon has not been used in any war campaigns. Well, that is probably enough information for you to wrap your head around. So until next time.